Hi folks, and welcome to my mountain lab, Vaptronics. And today we're looking at a Tenma 72330 35 megahertz dual trace oscilloscope. Now, as you can see looking at the scope, it's in fine shape, very nice looking, cleaned up very well. The case is in good shape, very minor abrasion or scratch of any type. Tiny little nick here, a little nick there, a little slight abrasion back there, but I doubt that you can even see them on the video. Clean. I like the look. The Tenma scope was made for more for the general public and general communications work, kind of thing you might find in an audio shop or a TV repair shop on somebody's home bench. You might find it in the industry, light industrial, things like that. They were not made to the military standards that you might have found a Hewlett-Packard or a Tektronix made to, but instead they were general communication standards, which lowered the price dramatically, made them a lot more available to the general using public. But it doesn't mean that the scope didn't perform well. It really does, and it's held up well, as we're going to see when we check through this. If you look at the back of it here, and here we see the back. You have some line voltage ranges and a Z-axis input on the back. And the serial number on this unit, by the way, is 3507569. Okay. And finally, we can take a look at the base of it. And what we're going to see, we have rubber feet and the front folding stand for the tilt stand. Quite nice. Alright, so we're looking at channel A right now. We have a 1 kilohertz signal coming in. Here we have it on 0.1 division, 0.1 milliseconds per division, so 10 divisions would be 1 millisecond, which would be equivalent to 1,000 hertz, which is what we have coming in. So we see one cycle across 10 divisions, that's 1,000 hertz. We'll check the intensity. We can take it from all the way dim to totally off. As we come up, we are at about maybe 10 o'clock, 11 o'clock, and we see the trace, and then I can take up to 12 o'clock. Here's 3 o'clock, and then at about 5 there. And then you have focus control. That's too bright. We'll take her back down, adjust the focus again, get nice sharpness. I'd say right about there is perfect. Okay, we're back looking at my scope, and as you can see, I've got a horribly skewed baseline here. Did that on purpose so I could demonstrate the trace rotation. There's a little slot right here with a screwdriver head, and you just turn that thing until you level that line right out. Definitely something you want to have working, so I wanted to be able to demonstrate this to you. But there you go. Works fine. As I take it through the ranges of the vertical input, let's see if we can. All right. at 5 volts per division right now with this signal coming in, very small signal. We're flickering a little bit, but as I go to 2 volt per division, I see the signal is locked in. 1 volt per division, half volt. So we have roughly a half a volt coming in, peak. Here's 0.2 volts per division, shows we are actually getting about 0.4 volts peak, or 0.8 peak to peak. Nice switch there. We went to 0.1 volt per division, shows there's 4 divisions up, that's 0.4, 4 divisions down, 0.4, so on and so on. And I wanted to point out that as I go through it, you see it switch nice and cleanly. The vertical switches have been cleaned inside to eliminate jitter and non-responsiveness. Same thing for the AC-DC ground connector, that's been cleaned up. The gain controls where you pull for ×5 gain. Let's get in a position where we can take a look at that. Okay, here we're at 1 volt per division. We know we're going up 0.4 and down 0.4. If I pull this, I get 5 times the gain. And what I'm going to see, if I position so I can read it, so I got 1, 2, 3, 4 divisions. 4 divisions times, I'm saying I've got 1 volt per division, so that'd be 4 volts. And then divided by 5 would be 0.8. 0.8 volt peak to peak, that'd be right. So that's working. Let's re-zero ourselves. Right there. We could switch to the B channel. We're going to need to switch our input. And right now you see we've lost our sync, but that's because we have our trigger source to channel A. We want to go to channel B. That'll give us our sync back. And we are showing 0.4 up, 0.4 down on channel B. Scope is responding very well. Okay, this time we're taking a look at channel B. We've got an input going in here. This is on the 5 millivolt per division scale. That's our most sensitive scale. We've got 1 division peak to peak, so that's 5 millivolts. And we're going to go ahead and test the ×5 gain. All right, center that, and we see that we are running 1, 2, 3, 4, 5 divisions. So we went from 1 division at 5 millivolts per division to 5 divisions, which is a gain of ×5. So we're getting the gain of 5 on B. I did have to readjust the position control to center the waveform when I went on to the ×5 gain. Alright, we're on channel A, and we're looking at 100 hertz signal. We're at 1 millisecond per division. 10 divisions would be 10 milliseconds, which would correspond to the 100 hertz. We see that we've started in the very right-hand corner and ended in the, left-hand corner and ended in the right-hand corner. One sweep, so that's 100 hertz, and it's what the scope would have us understand too. Let's go ahead and go to a kilohertz. Okay, it's a little bit harder to see at this point. Let's kill this light here. There we go. But we can change our time base from 1 millisecond to 0.1 milliseconds, and we should be able to adjust our scope just a hair. So we start in the right hand corner, and you see we end left hand corner, and again we end in the right hand, and that's for a kilohertz. Alright, let's go to 10 kilohertz. Alright, we are at 0.1 milliseconds. We're going to go to 10 microseconds. And again, we should see that we begin in the left-hand corner, one cycle in 10 divisions, we end in the right hand. That's at 10 kilohertz. 100 kilohertz, and we would go to 1 microsecond. Adjust our position control just a little bit to get us between the start and the end. There we go. And we start on the left hand side. We make one sweep in 10 divisions, and that's at 100 kilohertz. Alright, let's go to 1 megahertz. We could turn our intensity up just a hair. And we're going to go down to 0.1 microseconds per division. Again, we adjust our position control to give us our start and our end. Alright, so we played with our trigger a little bit too. And there we go. So we start on the left and we make a full cycle to the right. That's at 0.1 microseconds. 10 divisions would be 1 microsecond, which would be 1 megahertz. Now we're going to change our oscillator from the 3320 Hewlett Packard, and we're going to go to the PTS up above. Alright, get ourselves hooked up to the PTS, and we're going to start at, let's start at 10 megahertz. Alright. Okay, we adjusted our intensity a hair, we adjusted our focus a hair. We're at 0.1 microseconds per division. If we adjust our position control, horizontal position, so we start our curve or our cycle right at the center here, that's what I'm picking. I'm going to go up, down, and then come back up, and it does so in 1 division. That 1 division represents 0.1 microseconds, which would be 10 megahertz. So we have 10 megahertz. Let us try 20. All right. We're going to do something slightly different in this case because the cycles are so much smaller. We're at the limit of our horizontal sweep range. So we're going to count in 5 divisions. We're going to see if we have 10 cycles. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we finish on the right there. So we have 10 cycles in 5 divisions. That would be at 0.1 microseconds. So in 0.5 microseconds we have 10 cycles, which would be 20 megahertz. You could look at the single one if you wanted. We start right in the center. Let me turn this intensity up even more. Start dead in the center. Then we come down, hit this lower peak, come up, hit this upper peak, and then come back down. And we go back down, hit a lower, come up, and then come back down again. So we get 2 cycles in one division. That 2 cycles in one division means it's twice as fast as if it was going at one division, which would be 0.1 microseconds per division, would be 10 megahertz. We're going twice as fast, that's 20 megahertz. If we get 3 in there, we're doing 30. Well, let's take a look at what we got here. If I count 1, 2, 3, and back down. 3 cycles in a division, that's 30 megahertz. So our horizontal time base is working fine. I could switch to channel B and channel B right now, I see that I have, again, 1, 2, 3, and back down again. So 3 cycles in a division at 0.1 microseconds per division would be 30 megahertz. So we're showing 30 on channel B. Let's cut her back down to 20. We should see 2 now. Come up, down, and back again in one division. I see 1, 2 cycles, 20 megahertz. So our time base anyway is accurate. It's going to be this. It's the same time base on B channel as it is for the A channel. I'm not going to go through and redo the same verification on the lower ranges. So that's working fine. Time base is great. Our vertical volts per division, that's something we should look at. Okay, I've moved the Tenma to the top of my stack of voltage sources and my voltmeter here. And this is in an effort to just try and take you through some of the measurement linearity. Right now we're applying DC voltage. We're on our highest range. We're on 10 volts per division. And we see right now that we are 1, 2, 3, 4 divisions to the positive. And that would be 40 volts, which is what we have applied. Let's check our 0. Apply our voltage. Yep, we're right on the line. All right, let's take her down. 30, we're 3 divisions. 20, we're at 2 divisions. 10, we're at 1 division. And 0, we're at the 0 line. All right, let's go to the 5 volt per division range. Just our 0 just a hair here. Okay, and we're going to apply 5 volts per division. We have 4 divisions. We could go 20 volts. So let's go 20. And we see we're up 4 divisions. At 10, we're going to be half of that. That's 2 divisions. And then 0. Let's go to the 2 volt per division line. 2 volts per division on the vertical gain, and Let's apply 1, 2, 3, 4, 5, 6, 7, 8. So we tracked all the way up 8 steps, up 4 divisions. We went a half a division at a time, so that's working well. Let's take ourselves down to 4. Let's change our scale to 1 volt per division. We see we're at the top of the divisions. There's 4 divisions up, that's 4 volts. We're applying 4 volts. Let's step it down. There's 3, 2, 1, and 0. Let's go to 0.5 volts per division. And we have 4 divisions, we could go up 2 volts. Let's go up 1 volt, we'll go half scale. There we are. 2 volts will be full scale. And that's perfect. Let's go ahead and reduce our scale. We can go to 0.2 volts per division. We can go up 4 divisions, that'd be 0.8 volts. So we're going to go down a decade here, and we're going to go 0.1, 2, 3, 4, 5, 6, 7, 0.8 volts. No problem. Alright, let's bring ourselves back down half of that. Alright, we are right now at 0.4 volts. I'm going to change my scale to 0.1 volts per division. That puts us up the top of the scale, up 4 divisions, be 0.4 volts. Let's step ourselves down. 3, drop the division, 2, 1, and 0. Alright, let's go to 100, excuse me, this is 50 millivolts per division. Okay, 50 millivolts per division, and we're going to go up 0.1 volts, which put us up 2 divisions. And if we go up 0.2 volts, we go 4 divisions. Okay. Bring ourselves back down again. Let's go 20 millivolts per division. Alright, I've disconnected myself from the fluke because I didn't want to add the additional noise at this level. But I'm down to the 20 millivolt per division range, and we are right now 0 coming in, and I'm going to apply 0.01 volt. That brought me up a half a division. 0.02, 3, 4, 5, 6, 7, and 8 puts me right at the top. That's perfect. Alright, I'm now on the 10 millivolt per division scale. I'm using a probe going times 10 to my power supply. That means I can up my power supply by a factor of 10, because I'm going to divide it down by the probe, and my results will be exactly what I want. So let's see. Right now I'm I'm at 0. I'm going to go to 0.01 millivolt, 0.02, 3, 4. Alright, and then finally let's go to the last, that'd be 5 millivolt per division. That means I can go up to 20 millivolts, because I've got 4 divisions. And let's, we're going to go up 2 at a time, I believe. Let's go 0.01, 0.02. There we are. So we just went through the linearity of that scale to DC voltage, and we can see that it worked very well. We'll do the same check for channel B, since it is a different channel. And right now, we're on B, we're zeroing, okay? And we are going to apply taking off my times 10, I'm going times 1, so I'm going to be able to read. Here's 10 volts. We went up 1 division. 20 volts, went up 2. 30, went up 3. 40, went up 4. Let's go to 5 volts per division. Okay. And we will go 10. That should take us up 2 divisions. It did. And 20 would take us up 4. Let's go to 2 volts per division. Alright, I'm going to go up 1 volt. That'll take me up a half division. 2 volts gets me a full division. 3 volts is 1.5. 4 volts is 2 divisions. 5 volts, 2.5. 6 volts, 3 division. 7 volts is 3.5, and 8 volts is 4 divisions. So that's perfect. All right, we're on 1 volt per division. I'll go up 1 step at a time. 1 volt, 2 volts, 3 volts, 4 volts. Perfect. All right, we're on the 0.5 volt per division on channel B. And we are right now reading 0. And all right, we'll be applying 1 volt, which will put us up 2 divisions. 2 volts put us at 4. Okay. I'm going to go to 0.2 volts per division. And we're going to be applying 0.1, which will take us up half. 2, that's 1 division. 3, 4 is 2 divisions. 5, 6 is 3 divisions. 7, 8 is 4 divisions. Okay. 0.1 volt per division. And we will go 1 division, 2 divisions, 3 divisions, 4 divisions. That's 0.4 volts. All right, we're going to go 50 millivolt per division. If I go 0.1 volt, will be 2 divisions. If I go 0.2 volts, will be 4 divisions. All right, and we will go to 20 millivolts per division. And if I go 0.01 volt, that's 10 millivolts, will go up a half a division. 0.02 is 1 division. 0.04 is 2 divisions. 0.06 is 3. And 0.08 is 4 divisions. And I'm going to change my probe setting to times 10. Okay. And I'm going to drop down to 10 millivolts per division. And if I go 10 millivolts, I'll see the division. 20 millivolts is 2 divisions, 30 is 3, 40 is 4. Okay, and then finally, I'm down to 5 millivolts per division on the vertical, channel B. And if I go 10 millivolts, I'll jump up 2, and 20 millivolts will take me 4. So there's channel B. The linearity in DC is perfect as well. Okay, I decided I wanted to show you the calibration test point. This is a 0.5 volt peak-to-peak 1 kilohertz signal. We are right now at 0.1 division, 0.1 millisecond per division. And we have one full cycle in 10 divisions, which will put us at 1000 hertz. We are at 50 millivolts per division. We are in times 10 mode on the probe, which would put us at really 0.5 volts on the screen. So we have a half a volt, 1 kilohertz signal coming out of the cal point. So it's working. Alright, we're going to do a test here of the bandwidth of the scope. Right now I've got a 1 megahertz signal coming in. I'm using a probe on times 10. I'm on the 50 millivolt scale. We are receiving a signal that goes up 4 divisions and down 4 divisions. So we got 8 divisions at 50 millivolts. That's 400 millivolts, 0.4 volt peak to peak. Did I do that right? Let's see. 8 times 50 is 400. Yeah. Okay. So now what we're going to do is we're going to turn the frequency up from 1 megahertz to, here's 10, 20, 30, or 31, 2, 3, 4, 5. And this would be the spec bandwidth, is 35. And what I'm seeing that I'm just a little shy, like a half a, we are 0.1 division maybe shy. So let's back down on our frequency here. It's 34 megahertz, and that's 2.8 up, 2.8 down. So it looks like we're getting 34 megahertz out of our Y input. Let's go ahead and check input X. Okay, we are now on input X. We have a 1 megahertz signal coming in. And we are up 4 and down 4, just like we were a moment ago on the Y input. Let's go ahead and go to 10, 20, 31, 31, 32, 33, 34, 35. And what I see is I am 0.2 divisions off at 35. So let's back off. 34, 33, 33, yeah, looks like 33 is what I get out of the bandwidth on input X. So we are 33 on X and 34 megahertz on Y, and the spec is 35. Maybe a little bit of age, but we are very close and got good bandwidth. Alright, I've set up something just a little bit different here. For the Y input, I'm bringing in my output of my PTS 500, which is running right now at 2 megahertz. And for my X, or channel 2 input, I'm coming from my Hewlett-Packard 3320, which is putting out 1 megahertz. We can see both displays. Channel A's 2 megahertz is in the background. You see 2 peaks. You see them steady because I'm triggered off of that frequency. And then I can see the 1 megahertz as 1 peak shifting. for just a little bit of difference in frequency, the difference between the time bases. And what I'm going to do now is I'm going to put myself into XY mode. Right now we're in dual mode. We're seeing both channel 1 and 2 against the time base at 0.1 microseconds per division. If I go into XY, I get a Lissajous pattern. And that Lissajous pattern is telling me that channel Y has got 2 lobes for channel X is 1. So I'm twice the frequency of 1. If I know what channel X is by time base, that's 1. If I know it's 1 megahertz and then I see that I've got 2 lobes on Y, it means I'm running 2 megahertz. If I was to dial 3 on my PTS, I now have 3 lobes for Y. And if I go to 4, 4 lobes, and 5, and 6, starts to get a little busy, 7. Years ago, if you needed to try and determine the frequency of an unknown, and you had a known frequency, that you'd plug your known in on the X and you would do just this. And you'd figure out what your unknown was by comparing it and counting the lobes. Then we got frequency counters. That's your XY circuit functioning. It's doing just fine. Alright, we have a complex waveform on here, and we're going to try and demonstrate the use of the delayed and intensified function, the trigger delay. Let's imagine that this is a very complex waveform, and we would like to take a look at what's happening, say, somewhere right about here on that waveform. Well, we put ourselves in the intensified mode, make sure all of our buttons are in their minimum position. We have displayed the normal waveform pretty much, and we're going to try and blank out something that's up to the point that we're interested in by turning this trigger delay. Okay, and I say I want to take a look at what's happening right about there. Then what I do is I pop it in the delayed, push the delayed button in. And what it does is it now delays the trigger until we hit that point. And we're displaying what's going on from that point on the waveform. Then what I can do is I can turn my time base up and amplify that portion of the waveform. So I've now gone a couple of steps, more amplified into looking at that waveform, that portion of the waveform. So that's what that's all about. So really, I think we've just about covered everything here. Scope is working wonderfully. I've got a manual to go with it. Not an altogether easy manual to get, but it does take you through operation, theory of the circuit, and then it takes you through calibration, maintenance and adjustments. So it takes you through calibration. Then we have a series of fold-out diagrams. Show you the printed circuit layout and then the circuitry itself. So you have a complete package for operation and service. And I'll also throw in a brand new set of appropriate leads. Got a set on order, should be in here any day now. We'll have 40 megahertz leads for the 35 megahertz scope. should do you perfectly. So happy bidding. Thank you for listening, and good luck.